Hello everyone, and welcome to the third lecture of Intro to Nuclear Engineering. And today we're going to be talking about radioactive decay. So certain nuclei, so the nucleus of certain atoms, will spontaneously eject or throw out various other subatomic particles and or energy in the form of photons. And so this process of a nucleus ejecting some material or some mass or some energy is known as radioactive decay. And let's break this term down a bit. So the radio here here is because the nuclide radiates extra particles. Okay. The active part is because it releases energy and is a non-reversible process. That is, once the particle has been ejected from a nucleus, it's not coming back in. So we can say this as obeying the arrow of time in many cases. There are some forms of radioactivity that are reversible, but in general, there's a few and a couple of important ones that aren't reversible. And then decay is, the term decay is used because the parent nuclide is destroyed. Leaving one or more child nuclides. That is to say, in many cases, when you eject some subatomic particle from your nucleus, the nucleus actually loses something and is therefore no longer the same nuclide that it was before. So you have the parent-child relationship, or is one way to think about it, or is an analogy that a lot of people use. And so various different decay modes exist, various different ways in which decay happens. And those are all dependent on the parent nuclide. So what you have determines what pathways you can go to. So let's go ahead and start talking about some of those decay modes in particular. Okay, so decay modes. Can I do another line? No. So some of the decay modes of the one of the most common and most appropriate to talk about is what we'll call beta-minus decay. So beta-minus decay, this occurs when a nuclide has too many neutrons relative to the number of protons. Basically it's got too many protons in the nucleus, and so there's too much positive charge in the nucleus, and so other way around. It has too many neutrons. Beta-minus decay happens when there's too many neutrons relative to the number of protons, and so there's a lot of neutral particles sitting in the nucleus, and so it wants more charge density in the nucleus. So roughly speaking, if we want to think about this in terms of quarks, what we have is that we have, oops, let me switch tools. So we have N, a neutron we can think of as being equal to a proton plus an electron. So remember, neutrons are just a little heavier than protons, and electrons weigh about 1,000th the amount of a proton in a neutron. And so if you wanted to think about this in terms of mass differences or energy differences, it's not exactly true that a neutron is a proton plus an electron, but it's a nice way to think about it. And you can in the nucleus of an atom, when you have a beta minus decay, what you're getting is a beta is the proton. You're taking a neutron from the nucleus. That turns into a proton, and an electron decays and gets thrown out of the nuclide, and the nucleus remains with the proton. Importantly, about this obeys charge conservation. Right? So a neutron is a neutral particle. A proton is a +1, an electron is a -1, and so if you sum together, both sides have charge equals 0. So for example, we'd write something like this. So say we have oxygen 19, and this undergoes what's supposed to be an arrow, beta minus decay. On the right-hand side of this reaction, we'll get fluorine 19, F19. So that, right, so there's the A number didn't change, plus an electron, an E minus, plus this thing that why they're not exactly equal is that we also get an antineutrino. So neutrinos are denoted by the letter nu, and an antineutrino has the bar over it. So in addition to the beta minus, we also get an antineutrino. So it's charge neutral, and then the antineutrino is there to conserve the angular momentum of the system. So we won't be going into that right now, but that's why the antineutrino exists. So we have to conserve angular momentum, and we get this extra particle. The A number doesn't change, you get an antineutrino, and the charge doesn't change. All right. So that's one form of radioactive decay, or one mode of radioactive decay. Another one, which you could probably predict, is beta plus decay. So this is also known as positron decay. So this is the cousin or sibling of beta minus decay. So it's the complement, really, of beta minus. So beta minus decay occurred when the nucleus had too many neutrons. Positron decay, or beta plus decay, happens when the nucleus has too many protons. So the nucleus has too much positive charge, or has too high of a charge density inside of the nucleus, and so it wants to get rid of some of that charge. So there's too many protons relative to the number of neutrons, and so we do that by effectively turning a proton in the nucleus into a neutron. so it's similar to running the other process. It's the complement of the other process. Um, so say now we have oxygen 15 that undergoes beta plus decay. This will then turn into um, nitrogen 15 plus a positron, E positive, plus a neutrino, right? So we have an electron or a positron, E plus, and a neutrino rather than an anti-neutrino. So the anti-neutrino is there for the same reason. It conserves angular momentum during the decay. And so these processes are very similar, but you'll note that they're not necessarily reversible. You can't, in theory, if you had exactly a neutrino and a positron and an N15 coming in at exactly the right angles, you could get O15 back out, but that is incredibly unlikely and doesn't really happen. Neutrinos don't really react with much of anything. So, okay, so that being said, both beta minus both beta minus and beta plus have maximum emission energy. So let me write that down. Maximum energy. So this means that there's an energy above which no electrons are going to be emitted, and the spectrum looks roughly like a Poisson distribution. And so if I just draw this out, so the energy, basically the energy at which the electron is coming out with. So if we look at this, we have some energy curve here, and this is 0, so 0 energy is 0 velocity. So we want to know how fast the beta minus or beta plus is. And then this is the probability that something comes out, or an electron comes out with that energy. So let me maybe make that into, so I'll say P of E, so the probability of E. Then what we have is we've got this distribution. So there's some non-zero probability that it comes out at 0 energy at rest with respect to the nuclide. The probability goes up to some peak and then tails off back down and intersects with the x-axis. So this point right here is what we'll call E bar, so the max likelihood energy, and then this line here, this is actually what we'll call E max, or E sub max, right? So this is the threshold energy, the maximum emission energy, above which positrons and negatrons cannot come out at above. So for, oops, let me switch the key here. So for beta minus, the E bar, oops, should be a bar, is approximately equal to 0.3 E max, And for beta plus, E bar is approximately equal to 0.4 E max. Okay. All right. So that covers the positron and negatron emission that happen directly. However, if a nucleus has too many protons, it can steal an electron from one of the innermost shells. So it can electron, like the orbital shells in the atom. So it can go out and take an electron from one of the orbiting electrons, bring it into the nucleus, and then it would release you're effectively adding a negative charge to the nucleus, and so you release a neutrino, and this process is known as electron capture. Not election capture, that's something different. Okay, so electron capture, or sometimes abbreviated as EC. So just say this is when electron from atom's orbit is brought into nucleus. Maybe absorbed into nucleus. The nucleus. Okay. So here's an example of that. This does happen. So if we have carbon 11 plus an electron from the atom undergoes electron capture, this turns into boron 11 plus a neutrino. And so this is not a reversible process in particular. And because if it was a reversible process, the neutrino would be on the left-hand side of this equation. So a more famous example of this is our proton and electron and neutron system. So for example, if we have a proton plus an electron together, the proton can electron capture the neutron due to electromagnetic forces, and this would create a neutron plus a neutrino. Okay? But we also know that a neutron itself can decay into a proton plus an electron plus an antineutrino. So the cycle can't go indefinitely. Obviously, energy needs to be added to the system to create these neutrinos and antineutrinos, and you, in effect, always get this accumulation of neutrinos and antineutrinos, and there's trillions and trillions and trillions of neutrinos flowing through the universe, and they almost never interact with anything, and so they're very difficult to detect. There's neutrinos flowing through you right now. Okay, so that's sort of it for the beta decayers. So things that either electron capture or beta plus or beta minus. Another type of subatomic particle that is released is called alpha decay. Oops. So let me type that out. And so alpha decay is the emission of a helium 4 nucleus uh, from the nucleus, from a larger particle. So it's not a helium-4 atom, or it doesn't contain the orbital electrons, but it's just it's a particle made up of 2 protons and 2 neutrons. Okay, so that's what a helium-4 nucleus is. And so you have to have a certain mass, obviously, because you're losing 4 AMU roughly when this process when you undergo alpha decay. So this tends to be towards the higher end of the periodic table on the chart of the nuclides. And a lot of the actinides undergo this process. So for example, uranium 238, so this is element 92, will undergo alpha decay, and then this becomes thorium 234, right? So you lose 2 protons, and you also lose 2 neutrons, so you have a difference in atomic number of 4. And when this happens, of course, you also get the alpha particle itself, or the helium-4 nucleus. This is very common in nuclides above lead, where basically you have the neutrons and protons to spare. Okay? So alpha particle energy spectrum, so the energy that alpha particles come out at, unlike with electrons, they don't come out continuously. There's no instead they come out at discrete levels, right? So if we have E here, and then we have our probability as a function of energy, we'll just get individual lines with varying probabilities that an alpha will come out at that energy. And we typically measure this in keV, or kilo electron volts. And this is different than the betas, which come out with a continuous energy. And the reason for this is that there's no other particle, there's no neutrino in this system to have energy and angular momentum poured into. And so there's no smooth curve that you get. You just sort of, the alpha particle comes out with the energy it comes out in the direction that it's going to come out in. So this basically all of the momentum and energy are shared equally between the child nuclide and the alpha particle itself. Okay, so a real-world application of alpha decay is probably something that we're all familiar with, which is smoke detectors. Basically, the smoke detectors in particular will rely on americium-241. So, oops, let me go back. 241. Let's get rid of that. So, americium-241 will decay into neptunium-237 plus an alpha particle. And this is used to complete a circuit. So because you've got this +2 charge and it's a very heavy particle, You can imagine when everything's working properly, you've got a source here and a detector. Let me label these. Source and detect. Oops. So yeah, you have a source and a detector here, and let's make the alpha particles red, and so they go directly from the source to the detector. Okay. So in smoke. So however, oops, it's not a detector. So that's when everything's working normally. However, in the event of smoke existing, what happens is because these are so heavy, the smoke can come in here and disrupt the circuit. And so, and that will trip the circuit and make it so that these alpha particles actually don't, let me just try to select those. Oops. So those alpha particles don't make it all the way through, and instead they get stopped in the smoke because they're so massive and they have such a relatively high charge. So reliable, non-electrically triggered smoke detectors, or non-electrically reliant smoke detectors can use americium-241. So, okay. Next up, in terms of radioactive decay modes, is gamma decay. Oops. To be in black. So gamma decay is where the particle that we're emitting is light. Or we just have a photon that we're emitting. Since photons don't have a mass, this does not change the A number at all, or of the parent nuclide, and thus it is only possible between isomers, right? So we have a nuclide that, we may have a nuclide whose nucleus is at some excited state, and when it goes down to a lower energy state, or perhaps even ground, it will release a gamma, and that is, or a gamma and only a gamma, and that is what we call gamma decay. So typically we'll indicate an isomer or an excited state in particular by a star. So there's a very famous isomer of americium-242 has a well-known isomer that is or what they call metastable, so it stays around for a long time. And so we'll indicate that with an asterisk, and so this will decay down into the non-excited state, the ground state, of americium-242 plus a gamma. Okay. In fact, too, normally alpha decay and beta decay also release gammas. But what's different about the gamma decay here that we're talking about is that original nucleus must be above the ground state, and that no other particles are emitted. Okay. All right. So, additionally, or lastly, in terms of the decay modes that we'll be talking about today, there is what we call spontaneous fission. Okay, so this is when a nucleus just completely breaks apart. And we'll be talking about fission later in the course, but spontaneous fission spontaneous fission is when that breaking of the nucleus happens for no other apparent reason. It just randomly happens occasionally. It typically breaks into two primary children. Let's say two. So rather than having one major child and some other sort of particle, we get two primary children. And these are called a fission product pair. Okay. They also release an assortment of other subatomic particles like neutrons and protons and alphas and gammas. And alphas, betas, and gammas. So also, but they're not the major species. So also releases alpha, beta, gammas, neutrons, and protons. Okay, so there are a few examples of this in nature. And one manufactured species that does this, it's more common for manufactured species even, is Californium 252. So CF252, when it spontaneously undergoes spontaneous fission, it'll break into a fission product pair plus 4 neutrons. So for example, because it can be anything, it might break into 140, xenon 140, and Rutherfordium 108 plus 4 neutrons. And it's important to note that this fission product pair can be anything. There's some distribution again of what this happens to be, of what the pair happens to be. So I'll say, so the fission product pair that comes out, pairs have a bimodal distribution centered around half of the mass of the parent. Right, so you don't get more nucleons than you started with. You have a parent nuclide. It breaks into two. Those two pieces are almost never of equal size, but they would sum together to be about the same size as the parent. So to draw this out, let's put down some axes here. And so if I want to plot this as a function of atomic mass number, so A my A number and AMU over here, and we'll say the probability that I get that particular atomic mass number here, which is unitless because it's a probability. My distribution is going to look something, it's going to look bimodal. So there's going to be one hump at lower atomic mass units, and then another hump at sort of higher atomic mass units, and then that'll trail off. So this peak here represents the lighter species, and this peak here is the heavier one. Okay, cool. So we get some distribution. These distributions are different for every single parent. They're similar. We'll get into some of the similarities and differences a bit later in the course. And just as and so spontaneous fission is very common among the sort of manufactured species that are higher up, rather than the naturally occurring ones, although it does happen for some naturally occurring ones as well. So, and just as a bit of trivia, the word fission itself comes from Latin's findere, which means to split. So when you're thinking about fission, you can think of it as splitting an atom. And so fusion means to glue. So when people say the word fusion, it means to glue together the different parts of the nuclide. Okay, so in summary, we've seen a bunch of decay modes that exist. So I'll just list them here. So we've seen alpha decay, beta decay, both beta plus and beta minus, gamma decay, where we release a photon from an isomer, electron capture, where the electron is from an orbital is subsumed into the nucleus, and spontaneous fission. Now, these are sort of the major forms of decay that we are going to be looking at. There's, of course, other things that can be emitted as well. So you can have proton emission or neutron emission directly from the nucleus, but these are much more rare. They come up in rather particular circumstances. And so these are the ones that we'll be looking at in this course, more or less. Okay, well, thank you so much, and yeah, that's it for this lecture.